Okay, guys, let's begin the class then. Today we're going to start seeing the formal version of the chemical equilibrium, because the things that we saw last class, well, they are useful, of course, because that's the way, for example, in chemistry we see it and so on. But it's not easy to predict what is going on in what is going to happen in a reaction in equilibrium without doing experiments. And well, we have some background with the thermodynamics and the vapor-liquid equilibrium and so on that we saw already, like the activities and the fugacities and so on, that let us see how the real substances behave, right? So we're going to we're going to start seeing how the chemical equilibrium is treated using these kind of tools that we have at our disposal. Okay. So today we're going to divide this class in two parts. The first part will be a presentation about the fundamentals of chemical equilibrium using, of course, thermodynamics. And then I'm going to solve a problem about obtaining the equilibrium constants for a reaction. You're going to do either an Excel spreadsheet or any program that you want, for example, Maple or Mathematica or whatever you want, to solve that problem, to see that you can use different tools, different softwares to solve this kind of equilibriums, and that of course is going to be useful for your project, right? Because remember that at some point you have to tune up the reactor, right? The conditions that you want to use and so on. Okay, and the last part will be the different topics about chemical equilibrium that you're going to present as a class next class, the last class of the semester. So is the 22 of November. That's our last class. So in that one, you're going to present. So you're going to give class about a topic. Okay, and well, I will give you the specifications in a while. Okay. Any questions before we begin?
So in that class, like, we're going to give the topics?
Yeah. We have three different topics about chemical equilibrium, and you're going to present those topics, right? So with the information that you have already and information that I'm going to present today, you're going to be able to do that, okay?
Okay, like to say what we understood.
No, it's a different topic, okay? So I will explain.
A new topic.
Exactly, and you will explain, for example, how you do calculations in gas phase, chemical reactions in gas phase, another thing with multiple reactions and so on, right? Yep. But that is for the last part of the class. Okay, so let me share the.
But I think this is the last class.
Right, it's Wednesday. Supposed to be the final, the semester ends in exactly Wednesday. So
I think Wednesday is like the last class of all.
Exactly. Yeah, last class, and then the Thursday you don't have class of anything, right? Yep.
Mm-hmm.
Yes.
So yeah, that one will be the last class, right? And I told you already about the exam, right? That exam is going to be, let me see the date. I think we saw it already on the last class. It's Wednesday, the 19th of November at 4 p.m.
No, the exam?
Uh-huh.
Wait, it's 29th of November, no?
Yeah,
4 p.m.
Yeah, it's Wednesday, 29th. Yes.
29. Yeah, I heard 19.
No, sorry, maybe I said 29, sorry. 29.
Okay.
Okay, so give me a second and I will put the presentation, okay?
And today you will give us the topics for next class?
Yes, of course.
Okay.
At the last part.
And the guide for the final exam?
I will upload it tomorrow, I believe. Okay?
Okay.
Okay, thank you.
You're welcome, guys. Okay, give me a second. Okay. Now, can you hear me correctly? Everything's fine?
Yes.
Okay, so then let's begin the presentation. This is not just yet on Blackboard. I will upload it after the class. Okay, so is this the formal approach to chemical equilibrium? Okay. So we're going to see a couple of things that is common knowledge. Well, you've seen something similar to this in mass balance. That is called the extent of the reaction. But in this case, we're going to treat it a little bit differently. So we're going to speak about reaction. We're going to talk about the reaction coordinate. Okay. The coordinate of a reaction is how the reaction proceeds to the products, right? So you start in the reagents or reactants, and then how much of those reagents are going to react to form the products, right? So we're going to write down a general reaction. We're going to assign this new file, the coefficients, that is the stoichiometric coefficients, of course. Okay, we know those already. We know those already, and A1, A2, A3 are the chemical components, right? So of course, in each reaction, you can have different stoichiometric coefficients, of course. So for example, in this reaction, methane plus water reacts to form carbon monoxide and 3 moles of hydrogen, right? So we're going to assign a stoichiometric coefficient, so the new one, positive for the products and negative for reactants. We're going to use this further on to obtain the equilibrium constants, and well, with the equilibrium constant to obtain the amount of moles that we have of each of the components after the reaction reaches the equilibrium, right? So for this particular reaction, the stoichiometric coefficient for the methane is -1 because it's a reactant. Water is -1 because it's a reactant. Carbon monoxide is 1 because it's a product. And hydrogen is 3 because, well, we have 3 moles of hydrogen, right? Out there in the products. Okay, so this is just a convention because the way we're going to use the reactions for the equations. So it's the same thing as you knew from chemistry already. Okay? So of course we can see a change in the number of moles of any component. In this particular case, in component 2, with the stoichiometric coefficient, right? Because the reaction is balanced already, that change in the moles, in the fraction of the change of moles divided by its stoichiometric coefficient, should be the same for any of the products and reagents, right? That change should be the same. So if 1/2 of mole reacted in the methane, well, 1.5 moles of hydrogen should have reacted, right? And that is these coefficients, right, or these fractions, okay? So they mean the same thing. And we can extrapolate that, of course, to any number of components, right? So all the changes of moles of the components divided by the stoichiometric coefficient will be the same. So we're going to assign a change of the reaction coordinate. That's the way we're going to speak about this epsilon over here, right? So the differential of epsilon, the change in epsilon, will be equal to the change of the number of moles of any of the components divided by the stoichiometric coefficient. Okay. So in general, we can use this equation, right? So the change in number of moles of the component I is equal to the stoichiometric coefficient times the change in the reaction coordinate.
Teacher, what topic is this one?
This one is chemical equilibrium, but we have to speak a little bit about how to treat the fractions and so on using the reaction coordinate.
Oh, okay.
Teacher, so the reaction coordinate is like a rate of conversion of
yeah. Well, in the next slide, you're going to see that you have seen it in mass balance, for example.
Okay.
Let me show you, and you will see that it's the same thing. Okay,
thank you.
So exactly like in mass balance, right? We have, if we integrate this equation from the initial number of moles of the component I to the whatever number of moles of I at any point, right? And the reaction coordinate from 0 to the reaction coordinate, 0 because nothing reacted, or epsilon because it reacted to the equilibrium, you're going to find an equation that you have seen, this one over here. That is that the number of moles of the component I at any given point is equal to the initial number of moles and plus the stoichiometric coefficient times the reaction coordinate. In mass balance, we used to call this extent of the reaction. Okay, that is more or less the same thing, right? Is how much the reaction advanced, right? How much it reacted. So if we have more than one component, this is for one component, right? If we have for more than one component, we can say that the total number of moles of the system is going to be equal to the addition of the summation of and the number of moles of each component, and that one is equal to, well, the thing that we just determined, the reaction coordinate, right? So it's going to be the summation of all the initial number of moles of each component plus epsilon, or the reaction coordinate, that it's a constant, right, times the stoichiometric coefficients of each one, right? Okay, so then you have an equation that it's the total number of moles of that system is equal to the number of initial moles plus the summation, the additions of all the stoichiometric coefficients times the reaction coordinate. Okay, and with that information, we can obtain, for example, the mole fractions of any component, right? So the mole fraction of component I is going to be equal, as definition, is equal to the number of moles of the component I divided by the total number of moles, right? So using the reaction coordinate, we said that the initial number of moles of component I plus the stoichiometric coefficient of component I times the reaction coordinate divided by the total number of moles, the initial moles, plus the addition of all the stoichiometric coefficient times the reaction coordinate, that would give us the mole fraction, right? And that's it, right? That's an information that we're going to use. This is only for one reaction, right? This is for one reaction. Any questions, guys?
No.
No, so far. Thank you.
Okay. Okay, so this is just for one reaction, of course, any number of components, but one reaction. Okay, so what happens if we have more than one reaction? So let's say that we have J number of reactions, right? Okay, so any number of reactions. So to do that, well, we are going to do almost the same thing, right? The only problem is that we're going to have a stoichiometric coefficient for the component I in each reaction. Well, maybe in each reaction, depends on the reactions, of course. Times the change of the reaction coordinate in the J reaction, right? And that will be the number of moles, or the change in number of moles of the component I, right? So if we integrate that one from I and J, right, we're going to find that the number of moles, or the equilibrium, or the final number of moles of component I will be the initial number of moles plus the addition of the stoichiometric coefficient of component I in each of the reaction times the reaction coordinate of each reaction, of each J reaction. Okay, and of course we can extrapolate that one to the molar fraction of the components. So the number of moles of the component I in the system plus, for each reaction, the addition of the stoichiometric coefficient times the reaction coordinate for that particular reaction, and that one divided by the total initial number of moles plus the total stoichiometric coefficient times the reaction coordinate of each of the reactions.
Teacher, ¿qué dice antes del avance de reacción? ¿Es una J o una F? No, en el de abajo está BI y luego ¿qué es eso? ¿Una J o una F?
This one over here, this small one?
Es la que está antes de la E.
Ajá, J, yes, J.
J. ¿Y ese qué era?
The number of reactions.
Number of reactions. Thank you.
J, number of reactions, yes. Okay. Any other questions before we continue?
Yeah.
Okay. So we're going to, yes? Okay. So we're going to use that. We're going to use that equation, the last one, or the last part that we saw, for a quick example. So it says, consider a system in which the following reactions occur. Right, so methane plus water that reacts to form carbon monoxide plus 3 molecules of hydrogen, and a parallel reaction that is the methane times 2 plus 2 molecules of water that gives carbon dioxide plus 4 molecules of water, right? So this is, of course, reaction 1 and reaction 2, right? So J equal to 1 and J equal to 2. Okay. So it says, if there are present initially 2 moles of methane and 3 moles of water, determine the expressions for the molar fractions as a function of the reaction coordinate for reaction 1 and reaction coordinate for reaction 2. Okay, so please take a minute to copy that, and we can solve it in the next slide. Sorry.
So the first one says that in the first equation, we only have 1 reactant, and in the second one, J is 2 because we have 2 reactants.
No. Sorry again.
In the first one, we have J equals 1. That's J was the number of reactants, right?
No, reactions. So if you have 2 reactions, so we needed 2 J's, right?
Okay, reaction.
Yep.
Teacher, so in this problem, we won't calculate an actual number, right? We're just going to calculate like an expression.
Exactly. So we're going to leave an expression more or less like this one.
Okay.
Only for this particular system, right?
Perfect.
Okay. So do you have the information that you need?
Yes.
Okay. Well, maybe I can fit the information over here. Okay. So the initial number of moles, of course, NCO, will be just the number of moles that we have from methane and from water, of course, right? So we have 2 plus 3, that is equal to 5 moles of initial number of moles, right? And then we need to obtain the stoichiometric coefficient for each molecule or component. Right? So we can do the addition of all the stoichiometric coefficients for reaction 1. So it's 1, right? And this would be for reaction 1, we have CO, that is 1 because it's a product, so it's a positive, plus 3 of the hydrogen, minus 1 of the methane, minus 1 of water, right? So in this case, we have a 2. And we can do the same thing. Wait, sorry, that one was already down writing. So we're going to have for the reaction 2, right? In this case, CO2 is 1 plus 4 of water, sorry, 4 of hydrogen, minus 1 of methane, minus 2 of water, right? So 5 minus 3 is 2 again, right? And then with this information that we have, we can obtain all the equations that we needed, right? So for example, here we can obtain the number of the molar fraction of methane. So that is going to be equal, if you remember the previous slide, we have the initial amount of moles of that particular component plus the stoichiometric coefficient for reaction 1 times the direction coordinate and so on, right? So the initial number of moles of methane, CH4, it's 2, right? And then we have that it's the minus because we have it as a reactant. Okay, so the stoichiometric coefficient is minus 1. The epsilon 1, right? Because that's for the first reaction. And in the second reaction is it's a reactant 2, right? So and the stoichiometric coefficient is 1 again. So minus epsilon 2, right? That is the number of moles of methane at any point. and this we have to divide it by the total number of moles, right? So in this case, the initial number of moles is 5, so 5, and then we use these two equations, or these two values that we obtained here, right? This one and this two. Okay, so it tells us that it's positive in both cases, so plus. The stoichiometric coefficient for the whole reaction would be 2 for the first reaction times the reaction coordinate of the first reaction, and the same thing for the second one, because the stoichiometric coefficient that we found is 2 again, right? So 2 epsilon 2. Okay, so with that equation, we can obtain the number of the molar fraction of methane at any point, and we of course can do the same thing for all other components.
Teacher, so in the part of the total number of moles of the fraction, the sign of the numbers doesn't matter, because we have already taken that into account when making the sum of the coefficients.
Exactly. When we did this part, right? We take into consideration if there were negative signs, like in this case for the reactants, methane, and for water, right?
Okay.
And the products are positive because you're producing them, right?
Okay, so that's why we use the 2 like a positive number, because we already took that into account.
In other reactions, the addition of this, well, the addition of the stoichiometric coefficients will be negative, right? Because, well, depends on the reaction, right? Depends. If you have the reverse reaction from these ones, the hydrogen will be -3, right? You will change all the signs, and the final sign of the summation of all the coefficients will be negative, right?
Okay, perfect. Thank you.
So that one. Okay, so we do almost the same thing. The hydrogen, we started with 3, and then it reacted. For water, we started with 3 moles of water, and then 1 reacts in the first reaction, and 1 reacts in the second reaction. And the total number of moles is the same thing because it's the total number of moles, right? And this is for the reactants, and we can do the same thing for the products, right? So we can obtain for carbon monoxide, the initial number of moles is 0. I'm going to state it, as you don't have to write it down, of course. And then it's plus 1 is just in the first reaction, right? And that one over, well, the same thing as we did. For CO2, it's more or less the same thing because we don't have moles at the beginning, and this one only is a product in reaction 2 on the total number of moles. And it's these ones. And the last one, that is the hydrogen. We don't have hydrogen at the beginning, but we are forming 3 moles in the reaction 1, the reaction coordinate 1, and 4 moles in reaction coordinate 2, and that divided by the total number of moles. Okay, so any questions?
No, teacher, everything is clear.
Okay. Can I change the slide?
Yes.
Okay, so this was supposed to be the solution, but I skip it. Okay, so now we're going to use that couple of things that we saw already when we advance further. But right now we have to see what is the equilibrium criteria, right? The equilibrium criteria that we are expressing is that the Gibbs free energy in a closed system should reach a minimum, right, to be in an equilibrium. And that minimum, you can say that it's the minimum if you have that the partial or the change in the Gibbs free energy, it's equal to 0, of course, right? So this is like seeing a forward reaction, right? So forward reaction. On this one, the reverse reaction, right? So if you have that, at some point, the speed of the forward reaction will match the speed of the reverse reaction, and they will meet in an equilibrium, right? That's what we saw last class. So of course we're going to reach to a minimum point, and that should be when the Gibbs, well, the change of Gibbs free energy is 0, and that will be at some reaction coordinate that we're going to call the reaction coordinate at equilibrium, right? That's why we write down the E underneath. Okay. One thing to notice is that the Gibbs free energy is different from zero, right? It doesn't mean that here the value is zero. We're only saying that the change of the Gibbs free energy is zero. Okay, and of course we're going to make it dependent on the reaction coordinates, right? That's why we are going to use it, because and it's a very useful thing, because you only have one reaction coordinate for one reaction, right? So it doesn't matter how many reactants or products you have. We're only going to have one reaction coordinate for each reaction, and that's it, right? And well, this expression is, well, at the beginning it's just valid for, it's developed for a closed system. That changing the Gibbs free energy should be zero. But you can, if it reached equilibrium, if you open that system, it shouldn't change that much. So it doesn't change anymore, and we can assume that that expressions that we're going to develop are, you can use them for open systems too. Okay. Any questions on why we said that that should be the equilibrium criteria?
I have a question in why the change of the free energy must be zero.
Well, because, yeah, well, the Gibbs free energy tells you how much energy can be used to do something else, right?
Mm-hmm.
You can express it like that. So the change in Gibbs free energy is the change in Gibbs free energy is when the system is not changing anymore, right? It has the free energy doesn't change anymore because the system is not apparently doing anything, right? It's doing many things, but it's doing it in an equilibrium from the forward reaction.
Okay.
So that energy is not going to change, even if there are processes going on. Right? The forward reaction doesn't stop, and the reverse reaction either, right?
Yeah, I get it.
Yep.
Okay, perfect. Thank you.
When it says that the value is different than zero, it is referring also to the Gibbs energy?
Yeah, so the Gibbs free energy, this term, it doesn't have to be zero, right? We're looking for the change of the Gibbs free energy to be zero. The Gibbs free energy can have a positive value or a negative value, right? Just then the change is not going to change, it's going to be zero, right? That's what it means. You can have a negative change in the Gibbs free energy, but that one can be in equilibrium too, right? When the forward and reverse reaction meet at the same speed. Yep. Okay. Any other question, guys?
Thank you.
Okay. So we continue, right? So, so we're going to start seeing how can we model this, right? So at the beginning, we're going to fix in a single phase system, right? These, of course, are the easiest ones, and we have that the chemical potential, so mu E, of each of the components in the system should be, well, the addition of all those should be equal to zero, right? Because they're going to, well, be in equilibrium like in this place, right? So this addition is like the change in the chemical potential, and the chemical potential is related, obviously, to the Gibbs free energy. Okay, so our equilibrium criteria, we can express it like this too, right? That all the chemical potential of the products and the chemical potential of the reactants are in equilibrium. Okay, so that should mean that all the additions of those should be zero. Okay, and we saw it. Well, we just saw it with Claudia in solutions. In solutions that we can express the chemical potential using fugacities, right? So the standard fugacity and the fugacity in the solution, right? So this is the standard. This is in the system of that particular I component, right? So you can express this using the standard Gibbs free energy for the component I, that you can find those in tables, or you can calculate those using the enthalpy and the entropy changes, or the absolute entropy and entropy, and the chemical potential, right? So if we do this, well, we solve this equation for the chemical potential, and we do the addition of all the components in the reaction, we're going to have this equation over here. Okay, so what we did is that, well, we use these two equations, and what we have is that the addition of all the Gibbs, the standard Gibbs free energy of each component, plus how the fugacities are related from the standard ideal case and from the real case, right? And that, because of the loss of logarithm, is elevated to the coefficient, or the stoichiometric coefficient of that particular component in that reaction. If you remember, when you saw in chemistry and last class, you can say that the chemical, the constant of equilibrium, you can express it as the concentrations of each component and elevate those to the stoichiometric coefficient, right? If you have this. So this equation that we use in chemistry, it's derived from this other equation, right? From this one, using fugacities. Okay, so this is it's the same logic on it. It's only more complex because we're using fugacities and Gibbs free energies and so on, right? Okay, so that one, and then we can express this equation using the last equation, using the multiplication, right? Using the multiplications of each of the components. That this is the pi symbol. It's like the addition, only in multiplications of through all the coefficients, right? And we're going to multiply the relation between the fugacities, and that will be equal, of course, because we are in a relation with an equation equal to 0, to how the Gibbs free energy behaves in all the reaction. Yep. Questions?
What does the symbol you marked mean?
Which one, sorry?
The symbol, the last one you marked, that is like an...
Like a pi?
Yeah.
This one?
Huh.
This is capital letter P, and it's as this is the addition. So if you have, for example, nu E, and you have from E to the 3, you would have nu 1 plus nu 2 plus nu 3.
Yes.
Right? This one is for multiplication. So you have
okay.
from, let's say, I to 3 again, and again from nu, right? From nu I, right? So that one would be nu I, 1, times nu 2 times nu 3, right?
Okay.
It's just a way of condensing an equation, right? Any other question, guys? So again, okay. So then we reach to the equilibrium expression, right? The equilibrium expression is the last equation that we had. We're going to say that all this term over here, it's going to be the equilibrium constant. Okay, so that's why I'm writing it down here as K, right? So you see that this equation looks very similar to the ideal one over here, right? Or the one that we knew, right? The only thing is that instead of concentrations, we use fugalities, right? That's what it makes it more complex, and that's what will make it be able to use real systems. Okay, so of course we can do that. The equilibrium constant, will be equal to the exponent, because we have a. Now we're going to do the inequality from the constant, from the equilibrium constant, to the exponent of the Gibbs free energy divided by RT. And that one comes from this part and the natural logarithm over here, right? Okay. And then we can say that the natural logarithm of K is equal to the change in Gibbs free energy and the standard Gibbs free energy divided by the gas constant and the temperature, of course, right? And because we have standard conditions from this little symbol is the standard condition, that means that we are at 1 bar or 1 atmosphere, right? And then if we have constant pressure, then this K, the constant, the equilibrium constant, and the Gibbs free energy, the standard Gibbs free energy, depends only on the temperature, right? Because the other variable is already fixed. And then in the standard state, the standard state can change the temperature as long as it's the same fugacity. For example, if you say that the standard in this case is going to be, let's say, 100 Celsius, then you can do that if you want to, if it's more easy for the particular problem. For the particular problem, then the fugacity, the standard fugacity of the component I, should be at those 100 Kelvin, sorry, Celsius too, right? That should be maintained. The standard should be the same, 1 bar and the temperature, right? Most usually the tables that we have is at 1 bar on 1 atmosphere and 25 Celsius, right? That's the usual condition. But as you saw, you have energy balance class, right?
Yes.
Yeah, so in that one you saw how you can change the standard state, right? Well, the state where you begin your calculations, right? So depending on that, you can change this temperature.
Okay.
Okay, so that one.
Teacher, so this equation, let's say that it is like to relate the fugacities with the Gibbs energy, like it's the same K for both?
Yeah, the K is a constant, right? Like all the calculations that you have done with equilibrium, is you're assuming that the constant is it's a constant value, right? It's constant at a fixed temperature, right? If you change the temperature, the value of K is going to change. Okay.
And so changes fugacity and Gibbs energy.
Yeah, of course. Yeah, exactly. That's why, right? Because if you change the temperature, this fugacity of the component I in the solution is not going to be the same, of course. It's really equal, right? But you see that this doesn't. Is not dependent on the concentrations of it, for example. So if you change a concentration in a reaction, as we saw with the I forgot the name of that guy, the French one.
Le Chatelier.
Chatelier principle. The concentrations. If you change the concentration, you're going to shift the equilibrium.
The equilibrium.
The constant is going to remain the same as long as the temperature doesn't change.
Okay.
Yeah. If you change the temperature, yes, the constant is going to change. And that's one part that we're going to see in a couple of slides, how the temperature changes the constant, right?
Okay.
Okay. Okay. So this is just for you to notice because well, I suppose that you see it already, but when we talk about a change in a property, in a general property, let's say M, in the standard property, that is like saying that is going to be the addition of all the coefficients, all the estimated coefficients times the standard property of that particular component, right? It's the same thing as what we do with what we did with the Gibbs free energy over here, right? So it's the same thing for any other property. For example, for the internal energy, for the enthalpy, and so on. You can calculate all those, the change of that particular property using this equation, right? It's the same. Okay, so for the change of enthalpy, I supposedly you saw it in colligative properties. You saw that the Gibbs free energy is related to the enthalpy using this equation over here. right? That is called the Van Hoff equation. If you remember Van Hoff from for example, the lab, it's well, it worked with electrolyte solutions to see how much they change the properties, right? And that, well, part of that experimentation and that research led this relation, right? That the change in the standard enthalpy is going to be the constant gas phase times the temperature, well, the square of the temperature, and the change of the Gibbs free energy divided by RT when the temperature changes, right? So we can of course calculate the enthalpy using the specific heat of a substance, right? And we have values. Well, we have tables for specific heats of, well, thousands of components, right? For water, 1 calorie, or 4.186 joules per mole, and so on, right? Well, that's the constant one. Of course, we can have different parameters we are going to see in a couple of minutes. Okay, so the enthalpy can be calculated using the specific heat, and if we can calculate the change in the standard enthalpy, we can calculate the change in the Gibbs free energy. And with the change in Gibbs free energy, we can calculate the equilibrium constant. So using this equation and knowing that the K is going to be relate the Gibbs free energy, the change in Gibbs free energy divided by RT, we can have this equation that the change in the natural logarithm of the equilibrium constant with the change in time is going to be equal to the negative change of the enthalpy divided by RT squared, right? So here we can obtain how the equilibrium constant is going to change depending on if the reaction is exothermic or endothermic. Okay, so remember that if it's an exothermic reaction, we have a negative sign on the value of the enthalpy. Okay, so this term will be positive, right? Or the term of enthalpy would be positive because we have a negative in front of it, and then K will decrease, right? This value will decrease if the temperature increases, right? Because if the temperature increases, this value, the value here in the side 1 is going to be smaller, right? So that means that the constant should decrease. And if we have an endothermic reaction where the change in enthalpy is positive, we're going to have the inverse case, right? If we increase the temperature, then the equilibrium constant is going to increase too, right? And that's it, right? That's what should happen, depending on the type of reaction that we have. And that again, we saw it with the Le Chatelier principle when we talked about exothermic and endothermic reactions in the Haber-Bosch process, right? That it's an exothermic reaction. So what happens if you change the temperature in that system, right? Okay, so we can have this equation really easy if we assume that the change in enthalpy is independent from the temperature. That, of course, it's a big assumption, and it's not going to work. It's only going to work for a couple of systems, not for any, right? For example, when you have the temperature that changes a little bit, for example, let's say that the reaction is from 25 to 35 Celsius, well, you can assume that the change in enthalpy is not going to be too big, and then you could assume this equation, right? This equation over here that says that the natural logarithm of the relation between the equilibrium constant at one temperature divided by the equilibrium constant at any other temperature, at the temperature 2, is going to be equal to the relation between the change in enthalpy and standard enthalpy divided by the gas constant, and that one by the factor of 1 over T for both temperature, for temperature 1 and for temperature 2, right? This, if you look close to it, you're going to see that it seems like a linear equation, right? That is y is equal to mx plus b, right? it seems the same way, right? So y would be the natural logarithm of the equilibrium constant. M would be the delta H over R. X will be 1 over T. Right? And B, well, depends on the system. It's a constant, well, it's a value that where the y-axis is 0 and how the x intersects that one. Any questions for that part?
Teacher, in the M also includes the negative sign.
Yeah, you can include it. It doesn't matter too much. Depends on how you plot it. But yeah, you're going to find the same values. Okay. So using this as a linear equation, we can have a plot for many reactions, assuming that the change in standard enthalpy is going to be independent from T. So we can find a plot like this one. Okay. Well, in each of the lines, you're going to find a reaction. For example, down here you have that 2 moles of carbon plus 2 moles of hydrogen in gas form is going to give you ethylene, right? 1 molecule of ethylene, and so on for each one, right? Depends. And the slope of them tells you if the reaction is exothermic or endothermic, right? And then you're going to find on the y-axis the natural logarithm of the equilibrium constant, and on x, as we said, 1 over T, right? 1 over the temperature. So Kelvin to the minus 1 in units, right? So if you assume this, well, you can obtain the equilibrium constant of any of these reactions, at variations of temperature, right? In many different temperatures. Okay? Do you have any questions?
No.
So this is like using, well, doing experiments and finding each value for each reaction, and then you can have a plot like this one. Of course, there are plots that have more reactions than these ones, or organic reactions, or blah blah blah. Depends on the topic you're researching on. Okay. But that is for the ideal case, right? That we are saying that the change in enthalpy is not going to be dependent on the temperature. That of course doesn't happen all the time. So we need to use a way of doing fixing or correcting for the temperature, for the change in temperature. Okay, so we're going to go back to the definition of the Gibbs free energy. That's equal to the enthalpy minus Ts, right? So if we do for all the components in one reaction, right, with the addition and the stoichiometric coefficient for all parts, for the enthalpy, entropy, and so on, temperature, we're going to take it as a constant, so we can take it out of the addition. Sorry, it doesn't depend on the number of components. What you reach to that the change in standard Gibbs free energy is equal to the change in the standard enthalpy plus T times the temperature multiplied by the change in standard enthalpy, right? And I hope you have seen this. If not, I will send you an email where you can find where to find these relations. But from thermodynamic relations, we can find the change in enthalpy at any temperature using this equation, using equation 1 that we have over here. And that is that the change in standard enthalpy at any temperature, it's equal to the standard enthalpy at a fixed constant with a known temperature that is we're going to call 0, plus R, that is the constant, times the integral from T0, that is the same 0 as the standard enthalpy over here, to whatever temperature that you want. From the integral of that is the change in the specific heat for standard specific heat for the reaction, divided by R, and times the change in temperature, right? And the same, we can find something very similar for the change in standard entropy. Okay, so again, we are start at a standard as a standard state and a known temperature, and then we add a correction for the temperature, and we're going to say that this the specific heat at constant pressure, we're going to be able to change. Well, the standard heat tells us how difficult it is to change the temperature of something, right? Then we can relate it through the integral to the change in entropy or to the change in enthalpy. Okay, so we're going to use these equations to obtain the change in the Gibbs free energy. Questions?
I have a question.
Yeah.
Does the R is constant, right?
Yeah.
Okay.
Yeah, there is the constant is 8.314 joules per mole Kelvin, right?
Oh.
In thermodynamics for energy, we use it like that one, right? In those units, but it's the same constant that we use to calculate in the using ideal gas equation, that we can use it as 0.082 liters per mole, liters atmospheres divided by mole Kelvin, right? Yeah, that gas constant. Any other questions, guys?
Nope.
Okay, so if we put that all that into the standard Gibbs, in the change of the standard Gibbs free energy, we obtain this equation over here, right? And we can condense it a little bit, knowing that the change in entropy, the standard, and the change in the standard entropy at a fixed temperature is going to be the relation between the enthalpy and the Gibbs free energy divided by the temperature, the standard temperature, right? And then if we add that, we have this value, and we divide everything by RT, we find this equation. And this equation is the one that we're going to use. So it relates the standard properties with how the enthalpy changes because temperature changes, and how the entropy changes because temperature changes. And that's it, right? And this is the initial value for the Gibbs free energy. Okay, that's it, right? And we know that, as we said already, the natural logarithm of the equilibrium constant is going to be related to the change in the standard Gibbs free energy divided by RT. Okay, so we're going to express. We're going to take the pieces apart. Okay, so we can separate the equilibrium constant in parts of the equilibrium constant that we're going to call K0, K1, and K2. Okay, so K0 is just the exponent of the change of the standard Gibbs free energy at a fixed temperature divided by RT at the standard temperature, right? That is this part of the equation. Where am I? It's part of this equation. That one is K0. And then K1 is going to be the exponent of the change in enthalpy. And that one is this part over here. So this is K1. And K2 is, well, it takes into consideration all the change with temperature. Okay, so this comes from K2. So we can obtain each part of the K using these equations. For example, all the standard, if we have one bar and temperature 25 degrees, we can obtain these values from tables, right? So K0, we can obtain it at any point, right? K1, we can obtain it too, because the only other thing that we need is the temperature, and all the other data come from tables, right? All these standards. So we can obtain that again from tables. Okay? And the part that we have to calculate and depends on the components that we have is the K2, that it's the part that changes because we change the temperature, right? And here, well, we have the only part that we have that we can know through tables is the change in a specific heat at a constant pressure. That it's over here, right? And that's it, right? Everything else, well, it changes. Okay. So using the CP as values of constants of A plus BT plus CT squared and so on, right? We can obtain this expression where we're going to do the change in constant A, right? So the change in constant A would be equal to the addition of I for the stoichiometric coefficients of I times the A coefficient for the CP, right? And that same goes for the change of B and for the change of C and for the change of D, right? And to obtain, well, to have these equations a little bit more simpler, we are going to put a tau that is going to be a constant. That is just the division between the temperature at which we want the equilibrium constant divided by the standard temperature. So most of the time 298 Kelvin, but you can change it if you need to, or if you have information at other temperatures. Okay. So this one it's already integral. This is the CP. This was the CP, right? We integrated already into this expression. Okay, so this expression is integrated already. If you have a CP with another equation with another form, well, you only have to do the integrals from the general equation for K2, and that's it, right? And these particular values, these particular equations are from the Van Ness book. So this one, of course, is taking into consideration that all the CPs in the tables in the appendix are in this form, right? Okay, but you can do it with any other form that you have or that you need. Any questions, guys?
No.
I didn't understand really well what does delta A and delta B represent.
Okay. You see that in the CP, we're going to, for example, this is for, let's say for the component I, right? Mm-hmm. So we're going to have in the tables of CP, you're going to have three different, constants. 3 to 4 constants, right? A, B, and C, okay? Mm-hmm. So for the reaction, you're going to have reactants and products, okay? So yes. This delta is the change, well, how A behaves, how the coefficient A for the reaction, for the complete reaction.
Okay.
Yeah. So we're going to do an example, and I think it's going to be clearer, right?
Okay.
Yeah. So if it's not clear after the example, well, let me know. I will try to explain it further. Okay. So example time. So the example says. So the example says that we want to calculate the equilibrium constant for the vapor phase hydration of ethylene at 418.15 kelvins to 593.15 kelvins, right? That in Celsius is for 45, sorry, to 320 Celsius. From the theoretical data using Appendix C of the Van Ness book, right? So the first thing we need to know, of course, is the reaction on the products. The reaction is ethylene that has a double bond over it that reacts with water, H2O, in acid medium. That's why you have over here, that you knew already. And then this double bond breaks and water gets into the into the structure, and you have ethanol at the end, right? So if you see the equations that we're going to use, For example, we need the Gibbs free energy, the standard Gibbs free energy at the standard temperature, and we need that for the enthalpy too, and we need the specific heat, how the specific heat changes, right? So for that we need the tables. Okay. So for the tables, what we have is, if you go to the Van Ness book, I don't remember the page, but well, appendix C1, you're going to find this table. I just cropped the values that we needed for the heat capacity and the. So let me start with the standard enthalpy. This is the appendix C4, and again you have the information, right? So remember that to obtain the change in the enthalpy or in the Gibbs free energy, right? So the enthalpy at 298, and that's the temperature that we have in the table, right? That's our standard condition. Sorry. So the standard enthalpy at 298, you can obtain it through the reaction, the stoichiometric coefficients. In this case is 1 for each one, and we'll take into consideration if those are reactants or reagents, right? So again, products minus the reactants, right? Or just the standard coefficients that we have, that it's nu I. Sorry, I missed the addition. So we have addition from I to for the standard the stoichiometric coefficient time the enthalpy, the change in information enthalpy at 298. Right? So we do that exactly. So the first one is the ethanol, so minus 200. 100. That one is in joules, right? And then we subtract the other two because those other two are the reactants. So in this case, ethylene is positive. The change in enthalpy is positive, so we leave it as negative because it's a subtraction. And then we subtract the other value for water in gas phase because that's what the problem said. And then with this, we obtain the change in enthalpy. That should be 192 joules per mole, right? And we'll do the same thing for the Gibbs free energy, for changing Gibbs free energy at 298, and again is the addition of stoichiometric coefficients times the change in Gibbs formation energy at 298, and we do the same thing. So this one is minus 190, and then minus 68, 460, and minus 228, 572 joules. And that one gives us a result of 29 volts minus 8,378 joules per mole, right? Any questions of any of that data?
No.
All right. So now we have that. We have the standard Gibbs free energy, or the changing in enthalpy and Gibbs free energy. And with this table, we're going to do the change in the coefficients of A, B, and C and D for the reaction, right? So we're going to start with A, with delta A, right? The coefficient A in this case. So this one over here. So that one is again products. Let me write it down again. Last time. So the addition of the stoichiometric coefficients times the coefficient A. That one will be the product, that is ethanol, 518.
And all the stoichiometric coefficients are 1?
For this reaction, yes.
Okay.
Yeah, but just take into consideration for any of the for the reaction that you're calculating, and that's it, right? Just pay attention to it, and that's it.
No, es que no la había visto.
Okay, sorry.
Pero,
Okay, so then we subtract, because the coefficient is -1 for the ethylene, that is 1.424, and the same thing for water. And that gives us a change in the A coefficient of -1.376. And we do the same thing for B, that in this case will be, let me write down the value so you can see what you have to do with the table. In this case, 0.001 minus 14.394 minus 1.450. If you pay attention, it says here that the value that you have in the table is 10 to the 3 times B, right? So if you want to obtain B, you have to take this 10 to the 3 as a 10 to the minus 3, right? Because you're solving that equation, correct? So this one, you get 4.157 times to the 10 to the minus 3, right? And we do the same thing for C and for D, and for those we obtain C minus 1.610, 10 to the minus 6. For D, we obtain that atom minus 0.121 times 10 to the 5th. Okay, and that's it, right? In this case, of course, D, for the only one that we have information is for water, but we don't have information for the C value. This just as a fit for the experimental values, right? Okay, so with that information, with the change in enthalpy and the Gibbs free energy and the coefficients for the change in the specific heat, we can calculate, of course, the different parts of the constant K0, K1, and K2, right? So let me let me start here. So remember that K0 is equal to E, or the exponent, to the minus change in Gibbs free energy divided by RT, right? So RT0, right? The standard temperature. So if we substitute the data that we have, this will be the exponent of plus 8,378. We have it as a negative because we have a negative sign in there, and that's it. And here is 314, sorry. That's the R, and the temperature in this case, well, the temperature we're using the standard temperature, so it's 298.15 kelvins. Okay, and that one, if you do the operation, you're going to find that it's 29.3659, right? And then we have to do K1. K1, we obtain that is the exponent. I'm going to write down a little bit different so I can fix everything. I can fit in everything. So in this case, is the change standard enthalpy divided by the constant of the gases and the standard temperature, and 1 minus T0. Sorry, I forgot a minus. Or T0 over T. And of course, if we substitute the data that we have, we're going to find that is minus 4,000, then R, that is 8.3, and times 98.15, that is T0, and that one multiplied by 1 minus 298.15 divided by, this is the first temperature, the problem said it was 418.15, Okay, and we obtain a K1 of, okay, so let's, we obtain a K1 of,
Teacher, could you make the numbers a little bit bigger?
oh, yeah, of
Thank
course.
you.
Yeah, so this one is 4.951 times 10 to the minus 3. This is at 418.15 kelvins, right? And we're going to have a K1, or in this case, at 593.15 Kelvin. That is going to be equal. Just substitute everything the same, only changing this value over here. And you obtain that that value should be 1.01823 times 10 to the minus 4. Okay. Any questions for K0 and K1?
The K1 equation is the one that we got in the other slide.
Yeah, this one, right? Let me check it. This one over here, right? So it's the same one.
Ah, yeah, okay, yeah.
Yep. In here, if you pay attention, you see that K0 doesn't depend on, it just depends on the standard temperature, right? So you only have one K0, but
Okay.
it depends on each of the
Okay.
temperatures that you want to find. You have two different Ks, right? K1 for temperature 1 and K2 for temperature.
Okay, perfect. Thank you.
Yes.
I have a question here. You got that the value of K1 was 4.95 times 10 to the minus 3?
Yes.
And then you got the value of K1 at 593 Kelvin?
Exactly.
Okay, thank you.
It's during that temperature, right? Yes.
It's 1.01, and what is that number?
That artificial things. Let me correct
In
it.
K1.
It's an 8. Let me erase it and let me put another 8. I don't know the commands for this one, the keyboard commands to erase and that kind of things. Yep. Okay, so these are, well, K1 and K0, and the only one that we have to obtain is K2, right? Okay. So K2, I'm going to need a lot of more space because we need to add the CP, right? So
integrate?
No, because we integrated already in this slide.
Okay.
The equation that we have here, the K2, it's already integrated, so we don't have to reintegrate it, right? But again, if you have a CP in another form instead of the exponential form, you can use the general equation for K2, right? And you would have to do the integral of that particular thing. Okay.
Wait, but the integral is when we have CP, no?
Yeah, but okay, so let me change color so I can, it's easier to see it. Okay, so this equation, K2 over here, this one, that is the general equation for K2. Right? Is with any change of a specific heat, right? In any form that you have it, right?
Okay.
And the equation that it's underneath, this one over here for K2, it's using the CP as an exponential form, this one. Okay? And doing the integral of that one. Yes?
Okay. But I don't see like where is CP marked in the second formula or the integral.
But because we separated into variables of A and B.
B and yeah, entendí. Okay.
Yeah, because that one is just the integral of those, right? Values.
Yeah.
Yep.
Teacher Rodrigo.
Yes. What was the question?
Te muteaste, Lalito.
Can we use like any of them or to get K2?
What do you mean any of them?
There are like two formulas, right?
Okay, yes. Okay. If you use the exponential form, if you see this particular exponential form is the, I didn't wrote it completely, but the CP, it's equal to A plus BT plus CT squared plus, yeah, plus, sorry, this is in this next, this one over here. Yeah, D of T squared. That's what it says over here, right? In the caption of this table. You have the form of that CP, right? So that one, if you use it and you do the integral, you find the expression that we have.
Okay. Yes, sorry.
That one. That's why you have a natural logarithm over here, because you're you have in over t and so on.
Okay. Yes, thank you.
Okay, so we were just obtaining K2, right? So let me change to the color again, right? Okay, K2, it's a little bit more complex, right? Because it has many coefficients on it. So it will be the exponential of a lot of terms, right? The change in A, in the constant A, times the natural logarithm of tau, that is the relation between temperature and the standard temperature. And then one, tau minus 1 over tau, right? And this one, and then plus 1/2 of the change in coefficient B, and B, and then tau multiplied by tau minus 1 to the squared, and that's 1 over tau, and plus 1/6 of the change in C times the temperature. So this was temperature, not tau. Temperature squared. Then so then tau minus 1 to the square, that multiplied by tau plus 2.
Teacher, in this case, we will also calculate two different K2s.
Yeah, because
each for each value of t.
Exactly, is dependent on t, right? And then plus 1/2 of the change of d divided by square 2. And this one, tau minus 1 square. Over here, tau squared. Right?
Teacher, sorry, what was like our initial question? I understand that we have K0, K1, and K2.
To obtain the equilibrium constant.
We have to multiply them, right?
Exactly. Yeah. Remember that K, the equilibrium constant, is going to be K0 times K1 times K2, right?
Okay.
Yep. So we have to find those first. Okay, so if you substitute tau, tau is going to be equal, well, depends on each one, but if you remember, tau is T over T0, right? So T in this case is 418.15 divided by 298.15. That's one of the taus. That's why we are going to obtain 2 Ks. And if you do the substitution and so on, you obtain that the K2 for 418.15 Kelvin should be equal to 0.9860, and K2.
And tau will always be T over T0?
Yes.
Okay.
And the standard, remember that the standard can change if you have information at other temperatures, right?
Okay, and we will use like the same tau for the first K2 and for the second K2, or it changes depending on
it changes, right? Because this one will be like tau 1 for temperature, and tau 2 would be equal to
will be 593 over 2 and
exactly
285. Okay.
Right? Okay, so that's why you have 2 different Ks, right? And well, after you do those calculations, you can obtain, of course, this table over here. Okay, so this table over here tells us what is the temperature. So this is the standard temperature, 298, and tau of course will be 1 because you have 298 over 298, and that's it. K0 is not going to change. Is not going to change with temperature because it's the relation of the standard Gibbs free energy and then standard enthalpy. So that doesn't change. And then K1 is going to change because it depends on the temperature, and K2 again, right? So we can have different values. And if we do the multiplication of all those, K is equal to K0 times K1 times K2, we obtain the value that we wanted. That was the equilibrium constant at different temperatures. Okay, so in these reactions, you see, if we take into consideration that K is equal right now to, sorry, this one is 6O. Ethylene CH4 in the water. And you can relate the constant that you have to see in which one you're going to form more product. So this is, of course, just to see it quicker, right? You're going to present next week how to do it correctly, right? We're going to spend a little bit using this equation so you can see what does it mean the K to be big or small, right? So for this particular reaction, if you see the K at 298.15 is 29, so that means that you have more products than reactants. And for the other two reactions, for the other two temperatures, you have a small K, and that means that you have more reactants than products. So for this particular reaction, for example, the temperature that you should choose is, of course, 298.15 because it's in the one that you're going to obtain more products instead of more reactants, of course, right? In an industrial process, what you want is to obtain more products, not to have more reactants, of course, right? So, any questions?
Okay, so we want a big K.
Yeah, most of the time, yes.
Okay.
Well, depends if you have more than one. If you have more than one reaction, right?
Okay.
You want to minimize the
Number of reactants.
the subproducts, and you want to maximize the principal product, right?
Okay.
So yeah, that's part of what you're going to present next class, right? So any questions about what we did today?
No, I believe not.
No.
So this is like for the real case, right? This constant is for the real case already?
Exactly, is how to correct a constant using how it changes using temperature, right? Is the real case.
Okay.
Yep. Okay, so we're going to do a more or less quick activity, depends on your programming skills or Excel skills, if you want to, about doing this same procedure. So this problem that we did, so that we need to calculate the change in A, the change in B, the change in C and D for a reaction, and then to calculate the standard enthalpies and the standard Gibbs free energy, and to solve K0s, K1, and K2 using either, well, any program that you want. If you can use Excel, or you can use Mathematica, or you can use anything, right? The whole point of doing this is that you have the means to calculate the equilibrium constant for any reaction. You're going to change it over time because we're going to add, for example, multiple reactions, right? But at least for now, that you have a little software or an Excel spreadsheet that helps you to calculate the equilibrium constant, using this information. Okay, so
Okay.
give you 10 minutes or something like that to solve
Yeah.
this.
But it's the same problem.
Yeah, okay, well, the whole point is that in the Excel spreadsheet or in the program that you develop it as general as you can, right? So depends on the number of reactants. For example, you can do this software for a reaction of any number of reactants that you want. For example, you can say that there are 6, and many of those will be 0 right now because you don't have too many reactants and products, right? But do it as general as you can, right? So you can fill. The only thing you have to do is fill a table, right, with values, and filling that table with the CP, for example, or the enthalpies. You solve the K automatically, right?
Okay.
Yes, does it make sense?
I have a question.
Yes.
Like, what changes the number of reactants?
What change? Well, if you remember, we assigned a stoichiometric coefficient, right? So if that, for example, if you want to do this problem for a reaction with 10 different components, you can assign 10 different spaces, and the only thing that changes is the stoichiometric coefficient. If it's a product, it will be positive. If it's a reactant, it will be negative. And if you don't have more than, let's say in this case, 3 reactants and products, the other will be 0, right?
So what changes is like delta A and delta B and all that?
Exactly. You're going to have how to calculate delta A, delta B, delta C, and delta D, right? Give the spaces to put that information on the Excel spreadsheet, right? You're going to calculate the change in enthalpy and in the Gibbs free energy. Again, you need spaces to, for example, if you're going to do 10 different reactants, you need spaces for the 10 standard Gibbs free energy and the standard enthalpies, right?
Okay.
And
Where did we use the change in enthalpy?
The change in enthalpy, you will use it for the K0 and K1.
Is it? Okay.
Yep.
This presentation is in Blackboard, right?
Yes, the presentation, yes, but the solution is not.
Yeah, it's okay. Thank you.
Sorry, no, the presentation is not yet on Blackboard. If you let me a couple of minutes, I will save it and I will upload it so you can.
Teacher, can you put the other slide of where it shows the C4 table, please?
The C4 table?
So I can, yeah, so I can take a quick picture of
the.
No, C4, please.
C4, sorry. Oh.
Thank you.
Yep. So I don't know if you want to work. Well, we can work in any kind of teams that you want to. We can work in pairs, or you can work alone, however you want, guys. So if you want to make a team, just let me know your name, and I will assign you to a space. If you want to work alone, it's fine too. Whatever you want.
Gil, ¿quieres trabajar con pareja?
Sí, si quiere Ángel también.
Va.
Okay.
¿Quieres Ángel?
Pamela, Paul y yo. Pamela, Paul y yo. Okay, let me. Guys, can I explain you the activity that we're going to do for the last class? So you can.
Okay.
Easily. Let me share
Yes.
Okay, so last activity and we're done, like done. Okay, so you have to give class to your peers. That's the whole point. Okay, so the topics we're going to just let me grab a piece of paper to write down your name. Sorry for that. Okay, so the activity is like this. You're going to give class about chemical equilibrium, all the information that you need, or if you want to, you can use another resources too, of course. But in the Vaness, you have enough information in the Smith and Vaness that it's already on Blackboard in the sections of materials and libros and books. Okay, so we're going to do 3 teams. Okay, so 3 teams, and each one is going to be in charge of the different topics that are for the equilibrium conversion for single reactions. We have single phase and heterogeneous phase. So 1 for each team. And the last one is multi-reaction equilibrium. Okay. In the Smith and Van Ness, you have many examples. Okay, many examples that you can choose, or if you want to use another one, it's fine too. So a couple of things that you're going to need. You have to read about the relation of equilibrium constants to composition. It's one of the subtopics of the chapter, and that is about gas phases reaction and liquid phase reaction. Okay, so the activity, the thing I'm going to pay attention to and to grade is the exposition or the presentation of that topic. That topic you can spend around from 30 to 50 minutes to give the topic, depends on how complex or how or do it as completely as you can, of course. And you need to include at least one example in full, telling everybody how do you solve it and why did you choose those values and so on, right? The considerations that you need to obtain and so on. And you can share, for example, if you did an Excel spreadsheet for that particular topic, you can share it. You can share that software. And you can do one activity for the rest of the teams, for example, anything that you want. To be more a little bit more, how can I say it? A little bit more fun. I will count the creativity counts. Okay, so it's going to count as an extra 50 points in the activity. So if you are very creative and you do interesting activity, or you present the topic in a cool way and so on, I can give you those 15 extra points. And this particular activity, because it's bigger and so on, is going to count as 2 activities for the final partial. Okay. So, any questions on what do I want for this?
No.
Okay. So, if you can make teams and tell me which is going to be with who for this for the activity of the Excel spreadsheet, I have your names as here in the chat. But for this other activity for the class,
the same teams, no?
Yes, can we work with the same team?
Teams? But I don't know if I have 3 teams. I have José Eduardo, Paul, and Pamela. Pamela. Paul and Pamela. That's one team. Then we have Ram. Todo el grupo. Diego, Ángel, Gilberto. ¿Y quién me queda? Carlos y Alex. ¿Ya se me acabaron? No participan.
Yeah.
Carlos y Alex. Okay. So, to be more or less fair, because Carlos and Alex are alone, you choose your topic first.
Where do we gotta see the chapter in the book?
Well, you can more or less think which one is going to be more complicated, right? I know, okay. So I would recommend you the first one, single phase. Is that one fine with you? Right?
I think that is the more difficult one.
What, the single phase?
We want heterogeneous phase.
Yeah.
Hey,
Okay, no, so heterogeneous phase, you wanted to Jose Eduardo, Paula, and Pamela?
Yeah.
Okay, so that's the second one. So Diego, Gilberto, and Angel will get the multi-reaction equilibrium, right?
Equilibrium. Okay.
okay.
So any questions on what do I expect for the activity?
No.
Nope. Okay, so I will put you then into the rooms, and I will see you in a second. Pamela, where is the Lalo chat?
Sorry, but I asked for his mail and he didn't answer, so I was putting pressure on him.
Okay, that
Thank
one. Okay, let me do the breakout rooms, and I will see you in a second. So, José, Pamela y Paul en uno, Diego, Ángel y el otro, Carlos y Alex en el otro. So that one, see you in a minute over there.
Oh, bueno,
O sea, trabajo en equipo, ya.
o
A
sea, yo
ver,
lo hice para hacerlo más rápido. Pero...
Hola chicos.
ay,
Hello.
Oye.
Escribí como fórmulas, ¿no?
esto me saca de onda.
Que
Porque
aparezca yo de la nada.
llega como un ángel. Así como,
Como un demonio. Eso.
Entonces, ¿tú qué haces? ¿La loca cero? Y,
No, pues si quieren yo les voy como dictando o no sé.
ay,
O sea, para...
si quieres te voy leyendo los datos.
O sea, pero
Porque Paul quiere que todos contribuyamos.
A ver, espera.
¿Tienen
La
algún otro
H,
pregunta, chicos?
O sea, ¿qué es H?
H es la entalpía.
Ajá.
Porque la necesitamos para acá.
¿Lo van
Necesitamos,
a hacer en un Google
necesitamos
Spreadsheet?
necesitamos los coeficientes estequiométricos primero.
Ah, claro, sí es cierto.
A ver, vamos.
Es
vamos
uno de todos, es uno de todos.
a ver.
A ver,
Compound
hay que hacerlo como por
NI. Bueno, eso. N. I.
Esto lo voy a poner abajo porque esto va después.
Ya que no me hacen caso, me voy.
Pero no quiero preguntar.
Delta G y delta A y delta B es productos menos reactivos, ¿verdad?
Sí.
Ajá.
O sea,
Productos
puedes hacer eso o poner los coeficientes molares. Los coeficientes molares de los reactivos son con signo negativo.
Ah, ok,
Y
ok.
los
ok.
otros con...
los de producto compositivo, ¿no?
Dale. Hi, teacher.
Entonces,
Hello.
Hello.
Do we have to upload this to Blackboard, the Excel?
No,
Or it's just for us to have it
just for you to have it.
Okay.
Because you're going to need it. Key.
in the final exam?
For the project.
Ah.
And maybe for the final exam too.
Ah, okay.
Teacher, when do we have to deliver the third stage of the project?
The day of the
The complete project? Ah, okay.
Okay. And do we need to deliver it, to upload it to Blackboard or deliver it in paper?
No, in Blackboard is fine. We don't need to use paper for it.
Okay.
Any questions for you, Excel?
No, not yet.
Nothing.
No, yeah. I will see you in a second then.
Thank you.
Hello, guys.
Hey, teacher.
How are you?
Well, fine, thank you.
Do you have any questions for the moment?
About the homework that you just left, so we got to explain what it's in the presentation about the one-stage equilibrium reactions. Or...
Yeah, well, in the book, in the Smith Van Ness book, you have a section that is called exactly like that. It's
Okay.
called equilibrium conversion for single reaction, and the first part of that topic is the single phase reaction, well, the single phase equilibrium, right? So it goes in develops the the other part of the theory to obtain, well, to do calculations and to obtain the equilibrium constant and so on.
Ah, okay.
That's what you
Yeah.
have to. That's what you have to present.
And that's for next week.
Exactly. That's on Wednesday. Yes.
And the other question would be, when it's the final project due?
Now the final project due is for the final exam, the day of the final exam.
Okay, perfect.
Okay.
Yeah, I think that will be all, teacher. Thanks.
Okay. Well, if you need anything, let me know.
Sure. Thank you.
You're welcome.
Va.
Hello. Hola, hola.
Ari,
¿Cómo van?
te comparto mi pantalla para que veas nuestra preciosidad.
A ver.
¡Tarán!
Ya casi, todavía no llega, no llega. Ya llegó.
Esa columna no tenía caso que la pusieran.
¿Cuál?
La de temperatura 0K para el...
Ah, bueno, pero así ya no lo dejas bloqueado y ya que vaya bajando.
Solo tengo una queja.
No se mueve la... O sea, es que no hay forma
Bueno,
como de...
esa siempre va a ser constante, ¿no?
Ujú. Los demás bien lo hago para que no se vayan a mover como las referencias.
Ujú.
¿Sí
Pero
saben
pues
cómo
ahorita creo que no has
bloquear
puesto ninguna
referencias?
fórmula, ¿verdad? Con esta.
¿Eu?
Que si usan el símbolo de
Se
pesos,
movió.
pueden ajustar, o sea, que no se mueva la referencia.
Ah, sí.
No se mueva la casita.
Que sí la usé. O sea, es B16. Si quieres, déjalas así, Sunshine.
Solo tengo una queja.
¿Qué?
De lo que tienen puesto ahorita solo
No,
funciona
nada,
para los
nada
tres
más para...
componentes.
Aquí falta para otros dos compuestos.
Sí, acá.
Esas
O sea,
celdas las
este del
tengo.
tache.
Ah, ok. Usa para 5 compuestos.
No, estas ya están bien. O sea, según yo ya tienen como todos los datos en realidad como que necesitamos.
Ujú.
Me refiero más bien a tipo estas que están aquí. O sea, para bajarlas porque están estorbando a estos dos que... O sea, lo estamos haciendo para 5 para que no se encimen.
Ujú. Eso mero. Muy bien. Va bien, va bien.
Sí, depende de eso. Ah, bueno, sí. Sí, está bien.
Voy a ver cómo van los demás, chicos.
Ok.
La C. Entonces ya al final lo que hago nada más es dividir todo esto entre 6. Y ya.
Ajá, sí.
¿Lo están haciendo para 10 compuestos?
Es lo que hay.
sabe. Sí,
Ah, bueno.
ya sería todo. Deja.
¿Alguna duda, chicos?
No, hasta ahorita.
Todo bien en orden, profe.
Todo tranquilo,
Es
vale.
que- ¿Cuánto me decían que vale Tao? Porque
No entiendo por qué me la pone mal.
Chicos,
¿Por qué me la pone mal? Qué curioso. Qué raro.
¿cómo les va, chicos?
¿Mm?
¿Cómo les va, chicos?
Pues bien, nada más que no sé por qué no me funciona la fórmula en el Excel.
Pues compártela y te puedo ayudar.
Me escribí mal, no sé. Qué raro. A ver,
Compártele pantalla.
voy. Ahí donde me quedó. Ahí está. Sí. Sí. Es la K0, no sé por qué me la pone mal. No sé. Pero según la escribí bien.
Exponencial. Menos 1 por I5. 35.
Y 5 es la delta G de arriba. Justo arribita.
Pues sí, se ve bien. ¿No le sobra paréntesis?
No, según yo no.
¿Y si entiende exponenciales esa cosa?
Es que es lo que no sé, el exponencial si se pone así, ¿no? O sea, es XP, ¿no?
Es que en Excel sí se pone así, pero en Google Docs no sé.
Uy, híjole.
Bueno, si no puedes poner tal cual E y lo elevas, ¿no? O sea, con el triangulito. Creo que debe funcionar.
Déjame probar. Sí, sí.
Ah, claro.
Solo que pone E minúscula, ¿no? Porque si no, no puede malinterpretar.
Oh. Ay, no sé.
Lo estaban haciendo para cuántos reactivos y productos.
3 y 3.
Okay.
Órale. ¿Cómo se pone el triangulito?
Vamos a ver. Depende de tu teclado ahí, no estoy seguro.
Es Shift D con mayúsculas.
Si no hay en, ¿cómo se llama? Ahí en las fórmulas.
Uy, espera. No me salió el delta G.
¿Sí ya se dejó?
No, creo que no.
Siguen con el error.
¿Qué hice? No. Qué raro. A ver. Sí, también. Pues quién sabe. Y profe, la delta H está en joules, ¿verdad?
Sí.
Ok. No, pues no tiene por qué estar mal eso. No que yo sepa, no. No, sí está bien. Ahora tengo al revés. ¿Esta de cuál es?
No, sí, según la ayuda de Google, sí es EXP, el exponente.
Pues entonces, híjole, pues no sé qué le pasa. Que hay un error en la fórmula. No sé. O, a ver si le quito paréntesis. ¿Dónde se lo puedo quitar? No me lo tomará mal eso. No, sigue igual.
Qué raro. Y si nomás por molestar a vuelves a escribir, que sí está extraño.
Bueno, espera.
Sí, pues yo lo acabo de poner. Creo que lo tienes que poner en minúsculas. El EXP, yo lo puse en minúsculas en una hoja y sí funciona.
Está en minúsculas, ¿no?
Sí,
Entonces sigue mal, no sé por qué.
pero ahí sí tal vez deberías de poner entre paréntesis el -1, ¿no? Porque si
¿Menos
no,
uno?
está haciendo dos operaciones continuas y no sabe cuál va primero, y etcétera. Si no, aunque le pongas -i5 ya con eso. Pero bueno, también. Qué raro.
¿Quién sabe? Voy a ponerlo a lo mejor en un Excel normal, a ver qué pasa.
Ok, sí, porque sí, así dice que debe ser. La misma ayuda de Google.
Ah, qué bien, aquí se sale. No, entonces, bueno, ahí lo bajaré así, pero según yo en un Excel normal.
Bueno, si necesitan algo me avisan, ¿va?
Sí.
¿Ya hiciste la K2?
Voy a tratar de escribir la K2 de abajo, a ver si a mí me sale.
A ver, lo voy a tratar de escribir yo también, ¿ok? Exponente.
¿Sufren con la K2?
Yes. It's horrible.
You only need a lot of brackets.
Que se podría hacer, pero que hubiéramos puesto la tabla de manera vertical.
Sí,
Ajá,
pero si
porque
hubiéramos
así lo
puesto
podemos.
la tabla de manera vertical, o sería muy raro, o sería muy raro, porque todas las que se deslizaran, o sea, te haría muy complicado ver la tabla, porque sería excesivamente larga,
Sí, se ve mejor así.
o esa sería la otra, o no se podría hacer lo de los coeficientes de los reactivos, porque tendrían que ir en horizontal. Entonces, no sé si haya una manera, luego busco.
Y hágale.
Pues creo que ya no.
Punto. Sí, sí, dio.
Y pues ya nada más las
Ajá,
K.
96.
K es igual a esto,
Esos resultados sí no los copié.
esto.
Y están en el archivo que le subí.
Ah,
Ok.
A propósito, boom.
Y.
no, lo voy a abrir.
¿Todo tranquilo, chicos?
Sí, todo bien.
¿Ya se dejó K2 también?
Ya.
Sí, ya.
Ya.
Ya pudimos
Sí.
con cada.
Ah, pues ya quedó. Y con 10.
Esto.
Muy bonito.
Pues que Ángel, bro.
El comandante.
Está bien, se ve bien, así con 10 aguanta para casi cualquier reacción. Vale, me doy una vuelta en un ratito.
Ok.
Pues si no, mientras.
¿Cómo ven, chicos? ¿Ya se fue el exponente?
Ya.
¿Y qué le pasaba?
Es que como en en el Google Drive se tiene que poner comas en lugar de puntos para los números.
Ah, ¿en serio?
Sí, era eso nada más.
The more you know.
Eso sí debe ser una preferencia, ¿no? Porque nada más es cuestión de... O sea, eso es por país, ¿no?
Sí, según yo sí, pero
Bueno, el caso es que ya se dejó.
Sí.
Que es lo bueno.
Ay, pero cómo vio lata.
Sí, no, pues es que justo, nada más porque le buscas todos los errores normales, ¿no? No el que una coma o un punto sea el problema.
Híjole, ahora qué hice mal. Ujú. Falta un valor, ¿de dónde sale? Ah, ya. Esas comas, Dios. Ahora sí ya. Ahora falta nada más la K2. Híjole, a ver, vamos a... Uf. Ok.
Espera. Vale, me doy una vuelta en un ratito, chicos.
Sí, profe, gracias.
Sí.